So what I think we should do is give Katie another round of applause for taking technology.
Now we can actually get started. So has anyone I've got to mute Hangout. Now, hello? Okay. Right, we're back. It's a small echo, but I think we can manage it. Can anyone else hear it? Yeah. Okay, so has anyone in the audience ever come across an error page like this before, where it says, hang on a sec, our site's experiencing more traffic than usual, but you should be able to get back to shopping shortly. Raise your hands if you have. Right, so it's fairly common, and in fact, I did research about it, and users constantly face this type of error message about not being able to handle the level of traffic that's hitting their application. And as a consequence, users aren't able to make the purchase that they set out to make. Even on Amazon Prime Day, as I'm sure you can all imagine, there was a huge spike in user traffic on their site, and as a result, users were expecting a similar error page. They couldn't access the site to make the purchase they wanted to make. But going back to the jQuery experience, I have to be honest about it. I was slightly embarrassed, if not disappointed. When I visited this site, I was thinking about it as my personal user experience, not being able to make the purchase that I really wanted to make. But I never really thought about it from the other perspective. I build websites just like the ones above. And never once did I think, could my users be having a really similar experience? Hi, my name is Katie Koschland, and I'm an engineer. I work at the Financial Times, and today I'm going to talk about my load testing journey. And I'll aim to cover the core concepts behind load testing. First, I will discuss the challenge, and this is how I came across the topic of load testing. I'll then go on to explain what it means to load test your application and how you can get started with writing your own scripts. Then I'll go on to explain how you can use the metrics to help identify a performance issue within your application and discuss the tools and techniques we use here at the FT to help troubleshoot and improve overall performance. And finally, I'll conclude with some outcomes. So, the challenge. I recently finished a 3-month secondment in the Operations and Reliability Engineering team here at the FT, and they were developing the BizOps API. The purpose of the BizOps API was to provide a central store of all business information across the FT. So above illustrates the model and the type of information that could be retrieved from the BizOps API. As you can see, it contains information about our systems, how our systems relate to each other, how those then go on to relate to groups and teams and people who work at the FT. So it was really important for us to be able to understand the technical limits of our application, as it was going to be used frequently across the FT. So what was my challenge? It was about testing the technical limits of our Node application. But more specifically than that, could I answer the following 3 questions? Will our application crash? If so, can our application recover? And what exactly happens to the user experience? Once we've found the application's limit and pushed past it, does the user experience degrade gracefully, or does it just cause absolute meltdown? And I was told that the answers could be found by load testing our application. So What exactly is load testing? A colleague of mine recommended an excellent talk by Jad Mauchi, where he describes load testing in simple terms. It's about simulating ordinary user activity and then applying enough stress until it reaches failure. I really like this definition, but it kind of led me to my next question, which is, how can you apply that so-called stress to your application? So what you need to do is you first need to decide on a testing framework. There are many testing frameworks out there, including popular ones like Apache, Apache Bench, Locust, Artillery, Work, Gatling. The list goes on. But I decided to go with Artillery. It was for the following 5 reasons. First, it could be installed using npm, which was pretty nice if you want to get started quickly. Our application was in Node. Next, what it did was it allowed you to customize JavaScript code within your scripts. So this was particularly helpful where we needed to generate random write queries. So you could write a JavaScript function that was responsible for doing that, and then every time a virtual user was to make a request, you could just call that function and it would do the work for you. It was also helpful if you wanted to write a separate function that potentially could set headers or cookies for each of the virtual user requests. So above is an example and a snapshot of one of my JavaScript functions where you can see it's the function that sets the headers for each request made. So all I would have to do is import the function and call it within the script, and that would do the work for you. Another advantage was that scripts could be configured using YAML. I believe that really made the scripts easy to read and maintain. And above is a snapshot of one of the scripts I'd written. And you can see by writing it in YAML, it does make the scripts easy to read and maintain and can be used across developers. You can also see here that I'm calling the set headers function that I previously mentioned. And it's also targeted towards continuous integration. Unfortunately, I didn't have a chance to implement this, but this is something that's particularly interesting and I would like to do for future projects. If performance is a real high priority within your application, what you can do is you can configure your continuous integration, let's say Circle CI or Travis, and run your script each time you trigger a build. This way, you're able to detect at each point in your development process how a feature directly impacts the performance of your application. So it really allows you to detect any regressions within your application. And finally, it provides detailed metrics, and I'll go on to explain this shortly. But once you've decided on the testing framework that's appropriate for your application, then you can think about what type of requests would be hitting your application. So what your test scripts need to do is they need to be able to represent ordinary user activity. What I try to do is I think about the user journeys, the common user journeys that could be on my site, and try to capture those type of requests within my script. What you can do then is you're replicating the exact behavior in your script as your real users. Next, you need to decide on the shape of load that could potentially be hitting your application. You're probably thinking, what do I mean by the shape of load? And above is an example. It illustrates the shape of load that was hitting ft.com homepage during the 2017 election results. Slightly outdated, but it will demonstrate the point. So what you have is you have time across the x-axis and then the number of requests on the y-axis. So you can see how the shape of load changes over time quite drastically. So what you have is you have peaks where the number of concurrent requests per minute are incredibly high and then causing a huge spike in traffic. And then you have troughs where there's a significantly lower level of concurrent requests per minute, displaying a lower level of requests. So you want your scripts to be able to test the different types of different types of load that could be hitting your application over a production cycle. And this can be challenging. Before production, it's really difficult to predict the number of concurrent users and how they would ramp in over time. But it's really crucial in order for your test to be as accurate and robust as possible. So if your application's already in production, you might already know the shape of load that's hitting your application. A situation where you could predict the shape of load hitting an application is, for example, before the release of a push notification. Yesterday, the FT mobile app sent out a push notification to tell users about the fact that Deutsche Bank was starting to cut jobs with 18,000 at risk globally. And above, you can see the shape of load that occurred as a result of the release of the push notification. So before the release, the app was reaching a maximum of 1 million requests per minute. And very shortly after the push notification went out, it reached a maximum of 5.4 million. So you can see that it caused this significant spike in user traffic, causing more than 5 times the maximum load it was reaching previously. So in this script, we would know the exact shape of load we would want to be testing. It would be this short period of high spike in user traffic. But it's also okay if you don't know the shape of load. The BizOps API was in the development stage, and so it was really difficult to predict the number of concurrent users and how they ramp in. But I knew it was crucial if I wanted my tests to be robust. So what I decided to do was I decided to split my script into 4 separate phases. This way, what my script was doing was it was capturing the different shapes of traffic that could be potentially hitting my application over the production cycle. Depending on the size of your application will depend on how you define these 4 separate phases, but I'll talk through what I thought was appropriate for this scale of our application. So first I defined a warm-up phase, and this was an arrival rate of 10 virtual users per second, and that lasted for a short period of 60 seconds. Then I defined a ramp-up phase, and this was the idea of an arrival rate of 10 virtual users per second, which then would ramp up to 25 new virtual users per second, and that lasted for 120 seconds. Then I defined a cruise phase, and this was the arrival rate of 25 virtual users per second, and that was for the duration of 1200 seconds. And finally, I defined a crash phase, and this was the arrival rate of 100 virtual users per second for the very short period of 30 seconds. But it's really important to note here that there's no point hitting your application with a load that you know it can handle. The purpose of this phase is to really make your application crash. You want to be able to understand the exact behavior of your application once you've actually pushed past its limit. Once it's crashed, will the application be able to recover on its own? If so, how long does it take to recover? Or if it can't recover on its own, does an engineer need to come in out of hours to support and, get the application running again? You want to be able to answer these type of questions by, testing a crash phase within your scripts. And to visualize the 4 separate phases, what I've done is I've identified these 4 phases in a production cycle. So it's a graph again showing the number of requests per second hitting the ft.com homepage over a 24-hour period. So from 12:30 a.m. to 6 a.m., there's this very low level of 5 requests per second. And this is what I discussed as the warm-up phase. You then have from about 6 a.m. to 9 a.m. this gradual increase in the number of requests per second from 5 to 11. And clearly this is during our users' daily commute, and what I've defined as the ramp-up phase. Then, from 9 a.m. to midday, you have this constant rate of about 11 requests per second. And this is what I discussed as the cruise phase. And then what I've done is, obviously I couldn't make ft.com crash, but I've extrapolated the graph to demonstrate what I believe would be suitable for the crash phase for the size of this application. So that was about 40 requests per second. So now what you've done is you've made decisions on the testing framework, the type of request, and the shape of load that you'd want to be testing within your script. You're ready to write your first script. So let's discuss how you can get started with writing your own script. So what should it look like? The script should be split into two sections. So first you have the config section. And what you do is you start by choosing the target of your load test. So that's the API of the server under test. In our case, it was the BizOps API staging endpoint. Our staging endpoint was a replication of production, and so it was accurate to test staging for our load tests. And then what you can do is you can specify any plugins you'd like to use. So we use a plugin that allowed us to send our output of our load test to Graphite and Grafana. So Graphite is our data metrics store, and Grafana is the presentation and data visualization layer. And this really helped us to monitor the metrics over time, and later on helped with the troubleshooting of a performance issue. And then what you can do is you can define the load phases. And this is what we discussed previously about the number of concurrent virtual users and the method of how they ramp in. So above again is a snapshot of how you would do this. And finally, the processor. So this is where you would import any JavaScript files that contain functions that you would want to use in your script. So above is essentially a snapshot of that entire section of the script. So once you've done the config section, you then have the scenario section. And this is where you identify what the virtual user's behavior is going to be during the test. So you define the type of request that the user is going to make. So what you do is you start with naming the virtual user request. In this case, the request was going to retrieve a list of all systems at the FT and their corresponding properties. So by adding the name and providing a description, what you can do is you can quickly identify in the load test how many times that particular query was run. And then what you do is you define the flow. And this is the array of operations that a virtual user will perform. And in this example, what they're doing is they're making a post request with a JSON body that contains a GraphQL query to an endpoint. And you can see here as well that I'm calling the set headers function that I previously mentioned. So above is a snapshot. And it's important to note that you can add as many operations as you'd like to the array of flow. But again, this is just a snapshot, so this shows one of the operations. It's also important to note that if you wanted to, you could assign weights to the queries. So a weight allows for the probability of a scenario being picked by a new virtual user to be weighed relative to another scenario. We didn't need to do this, but above I've shown an example of how you could assign weights within your script. So let's say that users are twice more likely to make a request to retrieve systems than they are to query health checks that are live. So you could assign a weight of 2 to the first query and 1 to the second query, and it's as simple as that within your script. So once you're happy with your script and you've put the config and scenario section together, you're ready to go. So you run the load test by using the following command: artillery, run, file path, and the name of the file. Okay, so you've run the script. What actually happens after you run the script? Artillery will provide you with a summary report, and this contains detailed metrics that help analyze the behavior of the application when it's under load. So you start with scenarios launched. That's the number of virtual users that have launched a scenario throughout your test. You then have scenarios completed, and this is the number of virtual users that have completed a scenario throughout your test. Then you have requests completed, and this is the total number of HTTP requests and responses sent. Then you have requests per second. That's the average number of requests per second completed throughout your test. And then you've got status codes. That's the HTTP status code responses from each request that has been completed. And request latency. That's how long it takes the server to receive and process a request. And that's measured in milliseconds. So it's all very well understanding what the metrics do, but how can you actually use the metrics to help identify a performance issue within your application? So above is an example of one of the early summary reports from our script. And what you can see and what we noticed was that the request latency started to degrade rapidly throughout our test. It began 67.6 milliseconds and then suddenly ramped up to reaching a median request latency that exceeded 30,000 milliseconds. And this was really concerning because we were only sending on average 20 requests per second, and we were really expecting our application to be able to handle a much higher level of requests per second. So not only that, you can see out of the 6,000 scenarios launched and completed, more than 90% of requests received an HTTP status code 500, indicating the server was aware of an error or simply incapable of performing the request, or a status code of 503, indicating it actually just couldn't even hit the server. So the metrics about the response times, the throughput rates, and status codes helped identify a serious performance issue early on in the development process that would essentially stop the application from running. Okay, so now we have a performance issue. How do we go about troubleshooting the issue? More specifically, how do we find the culprit? How do we find the thing that's causing this performance issue? So what we did was we ran several tests singling out each of our queries and sending the metrics to Graphite and Grafana. And after a couple of attempts, or maybe many attempts, we found the culprit. It was this GraphQL query which was trying to retrieve the first 600 systems that had a bronze service tier at the FT. In fact, what we realized was we were reaching 100% CPU when running this query, and it was at the very low level of 10 requests per second. It wasn't even 20. As CPU is the central processing unit in the computer that does all the computational work, it was really concerning that we were reaching 100% CPU utilization with a significantly low level of requests per second. So this kind of led us to believe perhaps it was an application issue. So what we wanted to do was determine whether there was something in our code base that was causing the CPU to reach 100% utilization. So what we thought was a good starting point would be to generate a flame graph in order to profile the CPU usage. So what we did was we used the plugin 0x. And again, it could be installed using npm, so it was really fairly quick to get started quickly. What you would do is you would run the first command to install it, and then the second command, what it would do was it would generate the flame graph for you and open it in a separate browser. So above is the flame graph that we generated. With a flame graph, all the data is on the screen at the same time, and the hottest code paths are immediately obvious as the widest functions. But really annoyingly, there was nothing unusual being displayed. There was no single line of code that was using up the whole CPU usage that we could just try to fix. So we needed to think about what else could be causing this performance issue. So our database was a Neo4j instance, and this was run by GrapheneDB. So when a user makes a read query using GraphQL, it hits an execution layer. And in our case, it was this NPM module called Neo4j GraphQL.js. And what that does is it would translate the GraphQL query into a Cypher query. So if you take this query that was causing the performance issue, it would get translated into this Cypher query. And what would happen then is this would then send the request directly to our Neo4j instance. So what we decided to do was we decided to look at the configuration of that NPM module and see if we could identify a performance issue there. What we noticed was that the driver had a maximum pool size of 100 connections. And what this meant was that if a session tried to acquire a connection, but the pool size was at capacity, it would have to wait until a free connection was available. Otherwise, it would send an HTTP status code 503. This is behavior we were kind of seeing. So this seemed to suggest that perhaps, we could reach a performance issue if the number of connections were exceeding the limit. So what did we do? We increased the pool size to 300 and we decreased the retry timeout to 10 seconds to see if this would resolve the performance issue. But what we realized was we weren't even hitting capacity, so obviously that had no impact on the performance of our application. So we looked into the next thing, and what we discovered was that our queries were not being parameterized correctly when using the driver. And this would impact performance of the query as it wouldn't allow for the caching of statements within the Cypher engine. So a query plan would not be able to be reused, and that would hinder the performance of that particular query. So what we did was we parameterized the Cypher queries, and as you can see above, this is the example. But again, there was no improvement to the performance of the query. So what did we do? We looked at Cypher tuning next. And thankfully, with Neo4j, you're able to see how a particular query performs by prefixing it with profile. And this isn't specific to Neo4j. This can be done on many databases, for example, a SQL database. And we ran profile on that particular query that was causing the problem, and this was the output. What we're really interested to see here is the total number of database hits required for that particular query. And in this case, it was 14,213. So the objective of query profiling is to find a way in which you can reduce the number of database hits required to perform the task whilst keeping the output level constant. So one way to reduce the number of database hits is to create an index on the starting point of the query. So what we did was we created an index on service tier attribute in the hope that this would improve the performance. And we ran profile again, and it worked. It did significantly reduce the number of database hits, but it didn't resolve the performance issue. In fact, it didn't have an impact. So what we did next was we looked at the configuration of our Neo4j instance. What was the size of the instance? What was the RAM size? What was the number of cores on our server? This is what we were interested in looking at next. And what we did was we started by running system info in the Neo4j browser, and this provides information about the size of our database. And from this, what you can do is you can use the Neo4j hardware sizing calculator, and it made a recommendation to us. And the recommendation was to increase the size of total RAM, increase the number of cores on our server, and this would explain why our CPU was maxing out. We also realized that we were using a shared resource, and perhaps if we were in a dedicated resource, that would impact the performance. So what did we do? We changed the plan and we increased it to performance 1. This had 8 gigabytes of RAM, 2 cores on the server. And so we made the change and we felt fairly positive and confident that, when we run the script, this is going to work. This would be the solution. Confusingly, even with a dedicated resource, the overall performance not only didn't improve, but it actually got worse. So this kind of led us to believe that, perhaps it's a network I/O issue. So when the database results are queued for processing by CPU, that if the input output's limited, then the queue of database results will back up, potentially causing a struggling CPU. So that kind of was the direction we were going to next. So you're probably thinking, okay, you did all these cool troubleshooting techniques and, you tried lots of things out, but, come on, what was the actual fix to this performance issue? And unfortunately, from one day to the next, the performance issue just disappeared. We were all of a sudden able to make 25 requests per second without our application crashing and without any performance issue. So for this particular example, we were unable to find the solution to the problem. So why am I sharing this particular example with you and not sharing an example where, I significantly improved performance? And the reason is because what I learned was really invaluable, and I want to be able to share that with you. I've been able to build a personal toolbox with tools and techniques that will help me eradicate future culprits. But also, there were practical outcomes. First, we were able to measure, assess, and somewhat improve the overall performance of our application. By load testing, we were able to detect a performance issue early on, and as a result, dedicate time to help improve the performance of our application before it went into production. But we were also able to assess the reliability of our application. By load testing, we increased our confidence that our application could stay online given a certain level of traffic, and understood at what point we would need to consider scaling our application in order for it to stay online. And to conclude, if you want to fully understand the performance and reliability of what you're building, you should all be considering load testing your application. Thank you for listening, and we are also hiring, so either come and chat to me after or visit this URL. Thank you.
Cool, thank you very much. Load testing is always fascinating. I've always managed to avoid it, but I have had a database that once went bad overnight, and queries that took milliseconds took seconds, and nobody knew why. Do you want to take questions, or do you want people to come and chat to you afterwards? Does anybody have a question? Oh, yes, we have one here.
Hello, thank you for presentation. It was cool. When you configure the test script, how do you configure the throughput? Is it just arrival rate, which brings in the desired throughput for you, or you actually need to configure think time as well, like the time it takes between requests? Mm.
Oh, there's one at the back. Hang on.
Yeah, excellent presentation. You talked about the profile of the way you put your work together at the beginning. I thought it was quite interesting the way you did that. But have you thought about doing other types of profiles as well, which may not exactly mirror your workload? I'm thinking something like an endurance test or something like that. Or do you not consider those as scenarios that would benefit? You have actually done quite a lot of work there with all the fixes you put in. So, yeah.
Any more for any more? Yes, one here.
Thank you for the talk. That's great. And I'll be interested in hearing what limits does artillery have in terms of how many requests you can hit, and if like how does it work, because it makes requests from your machine to the remote.
Originally, when I set out to pick, what we wanted to use, that was something to consideration, about was that could potentially cause some sort of, it was such a low level of request per second, it didn't really have to research the capacity of the number of requests that you could make. But I'm happy to have a look and find out what the capacity would be. But because it was such a small size application, and I didn't really believe we were going to have this serious performance issue, it didn't really do that amount of research into the past as of the tooling performance associated.
Cool. Any more? No, we're done. Well, thank you very much. It was a really interesting talk. And when I used to work for a company that did load testing, we'd have these people come in and said, "Oh, I want you to load test it to X thousand users." And then during load testing, it would fall over after 10, which is quite funny. All right. Can we give Katie another round of applause? Thank you.